तो आइए आज देखते हैं application of first law of thermodynamics to closed system, non-flow system. Work done in the moving boundaries of a closed systems. Let we consider a certain gas constant in a piston cylinder as shown in the figures. Pressure exerted by the gas is P on the cross-section area of the piston is A. As you can see this in these pictures, you see clearly pressures we apply in a closed cylinders. Small dl is the small distance, a to b is the distance. Displacement work of the closed systems we can consider, we measure the displacement work of the closed systems. Work done by the systems is given by these formulas. Work done is equal to force into displacement, that is force is equal to pressure into area. As we know that pressure is equal to force upon area, apply cross multiplications, we get force is equal to pressure into area, into displacement is equal to dl. Dl is dl cube is equal to volume. As we know that dv is equal to a dl. A is the area is the length into breadth, and dl as we know that when we multiplied area into area and a small displacement dl, we get the volumes. So dw is equal to p dot dv. We can get pressure into small change in volumes. As we see that area is equal to 4 pi by 4 d square. Suppose gas expand from positions A to B, then work done by the gas is given by dw is equal to integrations of v1 to v2 p dv. As you can see that in these graphs, pressure and volumes graphs, a small change of volumes we calculate by these formulas. It was done by the systems, then it is considered as a positives. But if it is done on the systems, then W is considered as negatives. If heat is given by the systems, then it is considered as negatives. But if it is absorbed or gained by the systems, then it is considered as positives, as you can see that in this diagrams. And now the next applications, first is the constant volume pressures. As we know that constant volume is change in volume is equal to 0. Constant volumes heating process on PV diagram is given by work done is equal to dw is equal to pdv. As we know that dv is equal to 0, so work done is equal to 0. Apply first law of thermodynamics, we get dq is equal to mcv dt. As we know that first law of thermodynamics, dq is equal to internal energy plus product of pressures and volumes, change in volumes. So change in volume is equal to dv is equal to 0, so work done is equal to 0. As we know that internal energy is given by mcv delta t, so dq is equal to mcv delta q. As we know that in this constant volume heating process, a small change of heat transfer is equal to change of internal energy. You can see in this PV diagrams, constant volume heating process from the first law of thermodynamics, dq is equal to dw is equal to du. So du is equal to dq minus 0. 0 is dw is equal to 0. So du is the internal energy is equal to mcv dt. Change in internal energy mcv delta t, that is T2 minus T1. Now constant pressure process. In constant pressure process on PV diagrams, as you can see that work done is equal to integrations of PdV 1 to 2 from point 1 to 2. We get PB2 minus PV1. Here P is the constant, dV is equal to variables. It is differentiations of integrations of dv is equal to v integrate v a1 to 2 as we, so we get w is equal to mr t2 minus t1, that is work done is equal to mass into r is equal to rate constant है जिसकी वैल्यू होते है 8.413 and T2 minus T2 is the change in temperature. So as you can see that at constant pressures P1 minus P2 heat ups, so we get, now we find the heat supply is equal to integrations of mcp delta T is equal to mcp T2 minus T1. Applications of first law of the, according to application of first law of the thermodynamics, q minus w is equal to dw, du is equal to mcp T2 minus T1 minus mr T2 minus T1, du is equal to, so we get m is common and cp minus r and T2 minus T1 is common, so cp minus r, as you can see this, see that cp minus r is equal to cv, so cp minus r is equal to cb हो गया, du is equal to mcb T2 minus T1. Now constant temperature or isothermal process. In the constant temperature or isothermal process, the temperature is equal to constant, so delta T, change in temperature, is equal to 0. If an ideal gas follows the constant temperature process, then bias PV is equal to constant at temperature is equal to constant. As you can see that in thermodynamic, in isothermal process, you see that in this diagram, PV diagrams, work done is equal to integrations of PdV. Here we get volume V1 to V2 C dV upon V. So log work done, here we, so as you know that heat transfer in the isothermal process is 0. Now work done is, now we find the work done is equal to this PdV volume V1 to V2 integrate, now we integrate it, we get log V1 to V2, so we get P1 V1 log V2 minus V2 upon V1, we get same MRT ln V2 upon V1. Now change in internal energy, U2 minus U1 is equal to mcp delta T, that is T2 minus T1. Here T2 is equal to T1, so du is equal to, that is internal energy is equal to 0. So we get a heat supply is equal to work done, that is P1 V1 ln V2 upon V1. It is the final results in the constant temperature or isothermal process. Now reversible adiabatic process. In the reversible adiabatic process, heat supply is equal to 0, and as we can see that an adiabatic process is one in which there is no heat transfer between the systems or the surroundings, that is Q is equal to 0. It follows the law PV to the power gamma is equal to C, where gamma is equal to Cp upon Cv, Cp is equal to gamma Cv. You can see this in PV diagrams, the reverse adiabatics process, PV is equal to C upon V to the power gamma. Now we proceed. The reversible adiabatics process is shown in the figures. You can see this in these figures. Now we find the work done. Work done is equal to integrations of PdV. We get W is equal to C V to the power minus gamma plus 1 upon gamma plus 1, as we know that the integrations properties. We get W is equal to C upon 1 minus gamma bracket V2 to the power 1 minus gamma minus v1 to the power 1 minus gamma. That is, we get final work done is equal to W is equal to P2 V2 minus P1 V2 1 minus gamma. That is, we get C is equal to P1. We put this value of C. P1 V to the power gamma is equal to P2 V to the power gamma, as Q is equal to 0 for the adiabatic process. According to the first law of thermodynamics, Q is equal to du plus W is equal to D. As we know that first law of thermodynamics, Q is equal to internal energy plus work done. Internal energy is equal to heat supply minus work done. And internal energy is equal to minus W, that because heat supply is equal to 0. Internal heat supply is equal to 0. So internal energy we get P1 V1 minus P2 V2 upon gamma minus 1. That is adiabatic process. Now we proceed to the polytropic process. Here, now reversible polytropic process. In this process, it is similar to the adiabatic process, but here heat supply is not equal to 0. Let us see. In the polytropic process, both heat and work transfer take place, but in adiabatic process, work transfer take place but heat transfer doesn't take place. In the process equations is represented by PV to the power gamma is equal to C, where N is called the index of the process or polytropics index. That is, N is called polytropics index. The process is represented on PV diagram as shown in the figures. You see that work done in the adiabatic process is similar in the polytropic process. That is, W is equal to P1 V1 minus P2 V2 upon, where in adiabatic process gamma minus 1, but here in polytropic process N minus 1. That is, the N is the polytropics index. So change in internal energy is equal to mCb delta T. Now we get this. Now we find the work done in the reversible polytropic process. According to the first law of thermodynamics, Q is equal to W plus du. That is, heat supply is equal to work done plus internal energy. Q is equal to P1 V1 minus P2 V2 upon N minus 1 plus internal energy is equal to mCb T2 minus T1. As you can see that Q is equal to this Cp minus Cv is equal to Ra by the Maer's formula. R is the gas constants. As you can see that gamma minus 1 is equal to R upon Cv. We put the gamma minus 1 in these values, we get this. Q is equal to mCb T2 minus T1 in brackets gamma minus 1 upon N minus 1 plus 1. We get this. We get Q is equal to mCb T2 minus T1 bracket N minus gamma upon N minus 1. Q is equal to N minus 1 N minus gamma upon N minus 1 mCb T2 minus T1. For adiabatic process, N is equal to gamma, then Q is equal to 0. Suppose a process is governed by the equations P to the power PV to the power N is equal to C. It suppose goes from state P1 V1 T1 to final states P2 V2 T2. Then P1 V1 to the power N is equal to P2 V2 to the power N. By the gas equations, P1 V1 upon T1 is equal to P2 V2 upon T2 is equal to Mr, as we know that by the Boyle's law. If mass remain constant, then the equations 3 is applicable. That is, P1 V1 upon T2 is equal to P2 V2 upon T2. By solving the equations, we get P1 PV upon T is equal to C1. So we get Tn upon P to the power N minus 1 is equal to constants. That we get TV to the power N minus 1 is equal to constant. That is, P to the power N is equal to constants. Here we see that the applications of first law of thermodynamics for the closed systems. Thank you.